Was everybody able to open up yesterday's recording okay?
Yeah, I was able to.
Good, good. Glad to hear it then.
I wanted to remind you about my email. I haven't got any of the documents from the class. This is Victor Calderon.
Okay, let me see here. Victor, as soon as class is done today, I'll send it to you.
Okay, thank you so much.
Hmm?
My face is quite white right now, isn't it?
Is what now?
My face is super white right now, isn't it?
Yeah, a little glow in the dark, yeah.
Let's see if I can fix that. Oh, there we go. Fixed.
Good afternoon.
Christine.
Sorry for missing yesterday's meeting. I had a very untimely hair appointment that I didn't know about until the last second.
That's okay. Hmm. Okay, everybody. I think everybody that's planning on being here is here already. So,
Recording in progress.
so anyway, let's begin. And yesterday I left off by explaining to you that Earth is tilted 23.5 degrees. And what I left you with is what are we tilted 23.5 degrees from? Because we're basically talking about outer space here. So what are we tilted 23.5 degrees in relation to? A lot of this particular information we have only just discovered in the last 25 or 30 years because of improvements in technology. And what I mean by that is specifically telescope technology. We've actually been able to observe other solar systems in the process of being formed. And so between that and evidence we've collected here within our own solar system, we're pretty certain we know how our solar system came to be. And it essentially started out as a large dust cloud. The dust cloud that eventually became our solar system started out rather large. It was approximately somewhere in the neighborhood of 10 light years in size. The cloud would have measured 10 light years across. Many of you are not familiar with that term or what exactly it means, but 1 light year is the distance that light travels in a single year. Light is the fastest known thing to man. Nothing in the universe, according to Einstein, nothing in the universe moves faster than light. So light is the benchmark. It's what we use to gauge distance in the universe. And to put it in numbers that are, I think, a little bit more relatable, the speed of light comes out to approximately 650 million miles an hour. That's fast. And in a single year, everybody, light moves 5.8 trillion miles. So this dust cloud that I'm talking about was 10 light years across. So that's approximately 60 trillion miles of dust. And most of that dust is going to end up in the sun. Over 99% of all that dust I'm talking about is the sun. Much of it that was left over made up the planet Jupiter, and then the leftovers were the remaining planets, asteroids, and comets. So that's a big dust cloud, and that's a lot of objects forming out of that single dust cloud. But as it began to coalesce, as it began its process of creating a solar system, the dust cloud, which started out as a rather large, irregular shape, has always been rotating. It's always been spinning. So it's why this whole process takes so long, because that spin that I'm talking about, it will eventually become noticeable. If you were able to sit outside this big, huge dust cloud and actually watch it over a long period of time, eventually the spin itself would start to become noticeable. And here's what I mean by being noticeable. It was always there, but you didn't see it right away until it started to assume a certain shape. So it's the equivalent of an ice skater who begins their pirouette, their spin. And did you ever notice that as they bring their arms inward towards their body, they start to spin faster and faster? Okay, that's the laws of physics. That's not some ice skater magically coming up with a, oh, guess what I figured out? No, that's physics. That phenomenon of spinning faster when you pull in closer is a commonly known phenomenon. And this also happens to large dust clouds. So as the dust cloud starts to condense, the rotation becomes obvious to you. And as it starts to spin, it's going to eventually change from that irregular shape into a flat disc. It's the same thing as taking a lump of pizza dough and spinning it over your hand. The pizza dough becomes flattened. And so the solar system, the dust that's eventually going to make up our solar system, becomes a flat disk. Most of that dust is going to find its way towards the center and become our sun. And then the leftovers become all the planets, moons, asteroids, and comets. Well, several things are going to happen because of that rotation and that spin. Because it has now turned itself into a flat disk, this means that all of the planets are now aligned with each other along a flat plane. Okay? And so when we say we are tilted 23.5 degrees, what are we tilted 23.5 degrees from? We are tilted 23.5 degrees from the perpendicular. The word perpendicular is a mathematical term, everybody, that merely means a 90-degree angle. That's it. That's all perpendicular means, 90-degree angle. So if you have this flat disk of dust that's about to turn into a solar system, okay, and it is rotating, and if you are looking at it edge on, you are merely going to see an edge. That's it. This is perpendicular. Earth is tilted 23.5 degrees from the perpendicular in relation to the plane of the ecliptic. That's what this flat edge is referred to, the plane of the ecliptic. All of the planets in our solar system are measured against this plane of the ecliptic. We happen to be tilted at 23.5 degrees from the perpendicular. Jupiter is only tilted about 10 degrees. The planet Uranus is laying over on its side. It's tilted over 98 degrees. We suspect that early in the development of this solar system, the planet Uranus was hit on 2 separate occasions, and the planet was literally knocked over on its side. So it's rotating sideways. I mean, in other words, it's it's tilted 98 degrees from the plane of the ecliptic. This would be its north pole. And that's how it goes around the sun. It's the only planet that does that. There's one other anomaly amongst our planets. You see, when that dust cloud is rotating, as the planets form, they all rotate in the same direction because of that rotation of the big, huge dust cloud. Okay? So we rotate toward the east, so it gives us the appearance of having the sun rise in the east and set in the west. Now, that's true of every planet in the solar system. They all rotate toward the east because that's the direction of spin of the dust cloud I was talking about. There is one anomaly. It's the planet Venus. It rotates in the opposite direction from virtually everybody else in the solar system. The sun comes up in the west on Venus. And no, Venus did not, the dust cloud didn't somehow change direction. That's not what happened. The little bit of evidence that we have is that Venus also collided with another object, and it quite literally was a big enough impact that it stopped Venus's spin and caused it to start rotating backwards. And it's been doing so ever since. The spin is quite slow. As a matter of fact, a single day on Venus is almost as long as a single year on Venus. So it's part of the contributing factor as to why Venus is such a hostile environment. Venus is approximately the same size as Earth. We believe that sometime in the distant future, Earth is going to end up looking like Venus. And right now, Venus is completely incompatible with life. There is no chance in hell that humans are ever going to set foot on Venus. The atmosphere is made up predominantly of carbon dioxide or the CO2 gas. And the temperatures at the surface of Venus are in the 900-degree range because of that. And this is what I meant by Earth becoming like Venus. Greenhouse gases eventually, sometime in the distant future, is going to turn the surface of our planet into what Venus looks like now. So the temperatures are about 900 degrees, and CO2 is a heavy gas. We have CO2 in our atmosphere, but not near as much as Venus does, but it's a heavier gas than oxygen, nitrogen is. So standing on the surface of Venus is also deadly, not just for the temperature, but because the pressure. Standing on the surface of Venus, the pressure would be the equivalent of 90 Earth's atmospheres being on top of you. So if you were to land on the surface of Venus, it would be a toss-up as to whether you would incinerate first or be crushed to death. Either way, both of them would probably happen within 1 to 2 seconds, and you wouldn't know any difference anyway. So Earth is tilted 23.5 degrees from the perpendicular. On the diagram that I sent you, specifically the one that shows the Earth-Sun relationship, the diagram that has the sun in the middle and then the two Earths on either side of it. What I want you to pay attention to, everybody, you already know that the Earth is tilted 23.5 degrees from the perpendicular. When we go around the sun, everybody, that tilt in relation to the sun does not change. So when we go around the sun, we do so at this angle constantly. This is how we go around, like this. So as we move around the sun, again, this is all apparent from the surface of the Earth. As we go around the sun appears to move over the surface of the Earth. And I don't mean just by, daytime watching the sun go over the horizon. No, what I'm talking about is there is a spot on the Earth on any given day in which the sun appears to be a 90-degree angle over your head. There's only one place on Earth in which the sunlight strikes the Earth at a 90-degree angle. And that area of the Earth is called the tropics. It's basically the middle of the Earth over the equator. And if you happen to be standing inside the tropics somewhere, at some time during the year, you are going to witness sunlight at a 90-degree angle. Okay? However, that appears to move. So let's say, for instance, you are standing on the equator. At some time during the year, you are going to see sunlight at a 90-degree angle. But as the days pass along, the sun will appear to move. It won't be 90 degrees over your head. Now it'll only be, say, 85 degrees over your head. Okay? So it looks like it's moving. As we go around the sun on the diagram, everybody, I'm showing you two extreme positions of the Earth in relation to the sun. And one of them, as the sun or as the Earth is on one side of the sun in its rotation, okay, let's just say that it's tilted in such a fashion with the bottom end of the planet pointing more directly toward the sun. The sun will appear to be, in this diagram that I've given you, the sun appears to be directly over about this point on my pen. It's not exactly in the middle, everybody. It's pointing directly over the Earth at 23.5 degrees south latitude. 23.5 degrees south latitude places you approximately in Rio de Janeiro in Brazil. Here is what that means. If you are in Rio on December 21st, that's your shortest day of the year because you live on the northern half of the planet. However, on December 21st, the sun appears to be directly over Rio de Janeiro. The citizens living there are going to witness sunlight at a 90-degree angle at noon, because that's high, that's the old Western phrase, high noon. During any given day, everybody, the sun is at its highest in the sky at noon. Well, if you live in Rio on December 21st, the sun at noon will be 90 degrees over your head. And it's 23.5 degrees south. Now, December 21st is the shortest day of the year for us here in the north. It also signifies that we are heading into a new zodiac sign. So for those of you born in the winter time, you know that this is the sign of Capricorn. So the 23.5 degree line, south line, 23.5 degrees south, is known as the Tropic of Capricorn. 6 months later, when the sun or the Earth is on the other side of the sun, now the sun is pointing from this direction, and it appears to be pointing more directly over the northern half of the planet. And so the shortest or the longest day of the year for us in the north occurs on June 21st. And June 21st, well, if you happen to be at 23.5 degrees north latitude, you are in approximately Havana, Cuba. And if you happen to be in Havana, Cuba on June 21st at noon, you will see the sunlight at a 90-degree angle. After June 21st, we are now in the zodiac sign of Cancer. So the 23.5 degree north latitude line is known as the Tropic of Cancer. Everything on planet Earth located between 23.5 north and 23.5 south, that entire region is collectively known as the tropics. And it's the only place on Earth that will ever see sunlight at a 90-degree angle. I mentioned this to you yesterday, everybody. If you tell me that you saw the sun at a 90-degree angle over Visalia, I'd probably suggest that you find a god or a religion real quick and get close, because something awful has just happened in the cosmos and there ain't much time left. Okay. The angle at which you would see sunlight in Visalia or even Hanford, everybody, you guys are all located at 36 degrees north of the equator. So on December 21st, the sun is all the way down at 23 and a half. You are at the 36-degree north line. So 36 degrees to the equator, and then another 23 and a half degrees to get down to Rio. That is a total of 59 and a half degrees. The people in Rio see the sunlight at a 90-degree angle, but you here in the Central Valley, located at 36 North, are 59 and a half degrees away from Rio. So they see it at 90, you see it at 59 and a half degrees less than that. So on December 21st, over the Great Central Valley, sunlight only gets to be 30.5 degrees over the horizon. That's why you have short days. In the summertime, when the sun is directly over Havana, Cuba, which is 23 and a half north, you're still here in the Central Valley, but you're at 36 degrees north. The sun is directly over 23 and a half degrees north, and that means that the people in Havana, who see the sunlight at a 90-degree angle, however, you are 12 and a half degrees away from that. So you are going to see sunlight 90 minus 12 and a half. You are going to see sunlight at 77 and a half degrees on June 21st. So the range of angles in the Central Valley falls between 30 and 77. That's as good as the sun gets here in the valley. So why the heck is it so hot here in August and not June? There's actually it's the answer to it would surprise you a little bit, but it's right next door to you. The reason it's so hotter, it's so much warmer here in late July and the beginning of August, everyone, is precisely because you live next door to planet Earth's largest piece of exposed granite, and it's the Sierra Nevada mountains. Granite has almost the same heat retaining properties as your grandmother's cast iron cooking pots. You see, when you heat up a pot like that and then turn the flame off, it takes a while for that pot to cool down, doesn't it? Well, think about it this way: from December until June, the sun appears to be getting a little higher in the sky every single day until you get to June 21st. So metaphorically speaking, you're turning the flame up under the pot a little bit every day, every day, every day. And then you get to June 21st, and now your days are going to start to getting shorter. So after June 21st, you're going to start turning that flame down just a little bit, just a little bit, just a little bit. And so what happens is it's going to take that mountain range a few weeks to start giving up that heat that it had been absorbing between the months of December and June. Now it's going to start giving it up. However, the sun is still, even though it's shrinking, I mean, the angle is becoming less and less, it is still high enough in the sky that we still have relatively longer days here. And you're getting a double whammy of the sunlight and the heat being released from the Sierra Nevadas. If you haven't noticed this, everybody, if you are ever out in your backyard in the summertime during the evening hours, you might notice that it gets it's not a lot, but you notice it gets a little breezier at night than it is during the day. There doesn't appear to be any kind of wind or breeze during the day, but yet in the evening hours, there seems to be. What's happening is during the daylight hours, everybody, what happens to air when you heat it up? It wants to rise. It wants to go up like a hot air balloon. But then when the night comes along, that air cools down. What does cold air want to do? It wants to fall back down to the earth. So it's going to come tumbling down the side of the Sierra Nevada mountains, and it's going to pass over your neighborhood, and you're going to perceive it as a breeze. So it's nothing more than a night or day change in air temperature. And when air is heavier, it falls down. When air is hotter, it's lighter and it wants to go up. And it does this back and forth every day up the side of the Sierra Nevadas. It's why it's a little breezier at night than it is during the day. So anyway, what I need you to know is I'm talking about latitude lines here. The equator is the 0 degree line. I need you to know 23.5 degrees north and 23.5 degrees south. And I need you to know what their names are: Tropic of Cancer and Tropic of Capricorn. There's a reason why those two lines are 23.5 degrees, and I think it's pretty obvious to all of you why that is. Earth is tilted 23.5 degrees. Okay. There are two other latitude lines I would like you to know. And the first one is 66.5 degrees north latitude. That is the Arctic Circle. And 66.5 degrees south latitude, the Antarctic Circle. Okay. So everything is in relationship to the tilt of 23.5 degrees. 66.5 plus 23.5 is 90. Yeah, it's like when you go to the beach, everybody, many of us, we do not go out and try to get a tan right at noon now, do we? We oftentimes will either go out early in the morning or late in the afternoon. And even though those of you here in the Central Valley do not get sunlight at a 7 or 90 degree angle, the sun only gets to be about 77 degrees high here in the valley. And you know how much that hurts when you spend too much time out in the sun without proper protection. Okay, so can you imagine living under a 90 degree sun? I did that once in my professional career. I lived in the South Pacific for a couple of years working for a company, and I was bouncing between all of those little islands. And Kyle, I'm just as pasty white as you are. And after spending 3 years out there, I still looked pasty white. I got red, but that was about it. Didn't get much of a tan.
Yeah, I always get the mask on the eyes because the beard.
Oh,
So
right.
I always
right.
just get like this.
Yeah, I spent 3 years out there and I barely got any kind of a tan. My family barely noticed it when I came home. They're like, oh, so I went out and I recently discovered that there's a manufacturer out there, everyone, who makes t-shirts that provide UV protection to you so that you don't have to put sun lotion on. Is that cool or what? Anyway, so I need you to know those 5 lines of latitude for the first exam. Once again, they are Arctic Circle at 66.5 north, Tropic of Cancer, 23.5 north, equator, which is 0, 23.5 south, Tropic of Capricorn, 66.5 degrees south, Antarctic Circle. Now, latitudes themselves, everybody. Latitudes are the lines on the map that go sideways. They're lateral, okay? Lateral. Latitude lines go by a different name. They are also often referred to as parallels, because all lines of latitude are parallel to each other. Okay, that's why. If you use the word parallel in conversation, though, you should know that you are not discussing a point of navigation. You're not talking about a location when you use the word parallel. If you use the word parallel in conversation, you are probably referring to a political boundary. Parallel lines are lines on a map, everybody, are often used to create boundaries between countries and between states. So to give you an example, the border between California and Oregon is the 42nd parallel, or 42 degrees north latitude. That's how that works. The border between North and South Korea is the 38th parallel. Well, 38 degrees north latitude. So what that tells you is you're at 36 degrees north latitude. If you want to go up to 38 degrees north latitude, you're just a little bit north of Sacramento. Well, that's where the border between North and South Korea is located, 38 north latitude. And it's referred to as the 38th parallel. Now, when it comes to humanity's relationship to latitude, everybody, I'm referring to navigation. Humanity has been able to calculate and figure out latitude since the times of the ancient Greeks. To figure out your latitude, in the ancient times, of course, today with modern electronics, this is all moot now. But anyway, you got to remember, without modern electronics, the only things you had to guide you were the sun and the stars. That's it. So the Greeks were one of the first ones to figure out how to use latitude to navigate by. And here's what I mean by that. In order to solve a latitude type question, everybody, it's nothing more than the equivalent of 8th grade geometry, because what you're doing is you're measuring angles. That's it. You're just measuring angles. That's how you calculate latitude. It's not complicated. It's not calculus. It's just, what's that angle? And that'll tell you what the latitude is. Well, the Greeks were the ones who invented geometry, so it kind of makes sense that they're the first ones to figure this out. And there are two methods in order to do this, and it depends on whether it's the daylight or the evening hours. If it's the daylight, you have to do this at noon, because that's when the sun will be highest in the sky, remember? So you have this handheld device that you are putting up to your eye. And there's a small eyepiece, and the device I'm talking about is called a sextant. And I'm going to make a crude example of what it might look like here, everybody. Keep in mind, this is wooden, and it would be shaped a little bit like this. The flat pen here is pointing toward the horizon, wherever that is. This is going to be pointing toward the sun at noon. Whatever that angle is, that's your latitude. During the nighttime hours, you obviously can't point the damn thing at the sun because it ain't there. So what do you use in its place? The North Star. If you're not familiar with it, everybody, it's directly over the planet. Of all the stars in the night sky, the North Star does not appear to move. All the stars look like they're moving. If you stood out in your backyard all night long and stared at, say, the constellation of Orion, you would notice that from midnight until 6 a.m., it moved. It's not the stars moving, it's you rotating underneath them, but you get the idea. It looks like it's moving. The North Star is located directly over the North Pole of Earth. So as we rotate underneath all of those stars, we are actually pivoting underneath the North Star. And so it does not appear to move. And that makes the North Star a reliable reference point in the night sky. So you want to point that one part of the sextant again towards the horizon, and then the other part you want to point up towards the North Star, and that'll give you your latitude. That idea of measuring latitude, everybody, in such a simple fashion only works just so much. And what I mean by that, everybody, you're from, let's say for a moment, you're from the country of Greece and you're wanting to sail around the Mediterranean. So in the daylight hours, you're using the sun. In the night, you're using the North Star. There's no problems. You know your latitude. You know how far up or down. See, even though latitude lines run this way on a map, they're measuring this distance. Okay? So you know how far north or south you are. Let's take this to an extreme. Suppose you're one of the 16th century explorers. Oh, I don't know. Let's pick Ferdinand Magellan. He's the first explorer to completely circumnavigate the Earth. In order to do that, everybody, he had to sail his ship around the southern end of South America. You're all the way down near the Antarctic Circle. You are not going to be able to see the North Star in the nighttime sky because you are too far underneath Earth. The bulge of the Earth is going to get in your way and you're not going to be able to see the North Star. So the North Star, while it's good, it only works in certain places in the Earth, and that is in the middle. Once you start getting closer and closer to either the North Pole or the South Pole, then you start to run into problems, okay? Your accuracy level really gets bad. And keep in mind, everybody, these explorers that were landing in the New World during the 1500s, when they crossed the ocean, everybody, they really were lost because they had no ability to measure longitude. Longitude are the lines that go up and down on a map. However, they are measuring this distance. Okay? So once they left Spain, after the very first day, they had no clue as to how many miles they had just traveled in that day. None. And so effectively they are lost. They can calculate latitude. They know how far up and down from the equator they are. They cannot figure this out. Because figuring out longitude is not about measuring angles. That's latitude. Okay. So a little bit about longitude. Longitude are the lines on a map that go straight up and down, but they are measuring this distance. Okay. Each single longitude line on Earth is equal in distance to the circumference of the Earth. So every longitude line is 24,000 miles in length. That is not true of all latitude lines, but it is true of longitude lines. In order to solve longitude, everybody, you need a device known as a chronometer or a clock. That's how you solve longitude. It's done so with a clock. Clocks were not invented in Europe until the late 1500s. And can you imagine what that very first generation of a clock must have looked like? It was probably the size of the wall in your bedroom, and it most likely had a whole bunch of gears in it, and it was probably set in motion by a pendulum that was swinging back and forth. Now, here's the question: why did they not solve longitude? Can you imagine putting that kind of a clock on a small, rickety little ocean-going ship that is going to get tossed up and down by the waves? Is that clock going to physically survive the voyage? No, probably not. And even if it did survive, would it keep accurate time? Because in order to navigate with a clock, everybody, that clock needs to be accurate to about 1 second a month. So clocks built in the late 1500s were not up to the task. That is not going to happen. The clock is not going to happen until 1763. That's kind of odd, everybody. Mankind has known how to calculate latitude since the time of the ancient Greeks. And here it takes humanity until 1763 to figure out longitude. Why did it take them so long? Because the math involved is not hard. We've always understood the math. What the problem was technology and that clock. We had to build a clock that would be strong enough to put up with an ocean voyage and at the same time keep the accuracy that was necessary. And once again, that does not happen until 1763. So 1763 is kind of a pivotal year in European history, because if you are familiar with American history, everybody, between the years 1756 and 1763, Europe was involved in a war, and it was essentially England versus France. We here in this country refer to it as the French and Indian Wars. The Indians were sided with the French, and we obviously were sided with the English because we were still English colonists. And So most of that war that occurred between England and France did so on the open seas, not land battles. It was basically a naval battle. And here's why that clock is of importance at this time period. You are conducting a war against another nation, and you're doing so with your navies. So don't you think it would be a good idea that if you were going to engage in battle with your enemy, that you had all of your ships show up at the designated spot at the same time? Wouldn't that be kind of handy? Imagine sailing out to sea with 30 or 40 warships. You are heading out to sea for the purpose of engaging the enemy. Now, let's just say you're going to meet them at point X on the map. We're going to sail 2 days out to this place. We're going to meet the French Navy and we're going to destroy them. Well, you've taken off from England. Now it's going to take several days to get to your location. What happens if, let's say, it's 2 o'clock in the morning when it's really dark outside and the fleet has to make, say, for instance, a left-hand turn by, 20 degrees in order to get where they need to go. In order to send that message to all the ships, you had to light a fire and you had to signal the other ships. Hey, in 30 minutes, I need you to turn left and I need you to do so at a 20-degree angle. Do you understand? And then they respond, yes, yes, yes. Well, you've got 30 or 40 warships all attempting to make a left-hand turn at 20 degrees at the same time. That's not likely to happen all the time. You're going to end up losing 5 or 6 of those ships. They're going to get lost. So there is an urgency amongst the governments. We need to build this clock and we need it fast. So an Englishman by the name of George Harrison is the person who's going to build this clock. And Mr. Harrison is going to present this clock in the year 1763. And Parliament, the English Parliament, they had put up a bounty. Hey, whoever can build this clock, we have the equivalent of $1 million prize for you. So when Mr. Harrison turned in his clock, he himself didn't collect it. His sons did, because by the time he finished the clock, he was an old man. But the reason I'm telling you this story, everybody, is because the 0-degree longitude line, in honor of his accomplishment of building this clock, they ran the 0-degree line through his hometown of Greenwich, England. Greenwich, England is today a suburb of London. So that's where the 0-degree line is located. It didn't have to be Greenwich, England. There's no rule in the cosmos that says it couldn't have run through Kansas City or Shanghai, China. It was just that this gentleman built the clock. And to give you some idea of how good he was, everybody, that clock is in a museum today in Greenwich, England. And if you ever visit London, it's nothing more than a 15 or 20-minute double-decker bus ride to get to Greenwich, because it's a cute tourist destination today, because it still has its Renaissance appearance, with the cobblestone streets and all of that. But the museum that houses that clock is in Greenwich. And there's something rather annoying about that clock when you go to visit it, everybody. You see, the city elders decided that in the main boulevard that runs through Greenwich, They have embedded a copper strip in the street. So imagine, if you will, on Mooney Boulevard, they ripped up that center divider and then placed a big copper strip right there, okay, embedded in the cement. This is running through Greenwich, and if you follow this copper strip, it will lead you to the museum where the clock is. And that copper strip is the 0-degree longitude line. So what American tourists like to do, and this is what's embarrassing, they go out into the middle of the street and they stand over the top of that copper strip in the middle of the street, and one half of their body is in the Eastern Hemisphere and the other half of their body is in the Western Hemisphere. And they got their wife standing out there too. Hey, Gladys, take a picture of me. So it's not unusual to see a news story in the English news that night about some stupid American tourist who got hit by a bus and is now in the hospital with a broken leg. It's crazy. But that clock is still in the museum, and it still keeps time to this day of 1 second a month. That clock is 250 years old, everybody. That is impressive. That is craftsmanship at the highest level, because that clock does not have a battery and it does not have an AC cord. That's a wind-up clock. And it still keeps accuracy to 1 second a month. Before I became a teacher, early in my professional career, I was an electronic engineer when I was in my late 20s and 30s. And the company that I worked for at the time, and this is why I was in the Pacific on these islands, the company that I worked for put up into orbit the GPS system. And the GPS system is in your phone, everybody. It's the app that you guys use to locate your friend's house. It gives you your driving directions, okay? How that does that is because Earth has 24 navigation satellites orbiting around it. Each of these 24 satellites is in what is called a synchronous orbit, which means, everybody, that the satellite sits over one spot of the Earth and doesn't appear to move. In other words, it rotates at the same speed as Earth. So be for the same spot. And we've got 24 of them surrounding the Earth, all rotating at the same speed as the Earth. It took us the entire 1980s to put that system into place, and it had nothing to do with launching satellites. Once those satellites are in orbit, everybody, they have the same issue as the sailors on the ocean, and that is timing. If you want to solve latitude and longitude from outer space, it's all about proper timing. So each of those 24 satellites has on board an atomic clock. And the atomic clocks are accurate to about 1 microsecond every 300,000 years. I'd call that accurate. And the problem with it is Mr. Einstein comes into play. You see, those satellites in space are in what's called a zero gravity environment, and time moves faster in a zero gravity environment. So the clocks on those satellites are actually physically moving faster than they would here on the surface of Earth. So once we launched all 24 satellites, it's going to take us about another 5 or 6 years to go around the world calibrating the difference in time between those satellites and your phone on the ground. So for about 5 years, I was that guy from the Verizon commercial that instead of, hey, can you hear me now? I was like, can you find me now? Can you find me now? And so we did a lot of traveling around the world, calibrating those 24 satellites. So it's all about timing. And the only reason the 0 degree line runs through England is because the guy that built that clock is from England. That's it. That's the only reason it's there. So on the exam, everybody, I do need you to know that the 0 degree longitude line is also known as the prime meridian. Longitude lines are known as meridians. Longitude lines also have a second name. They're also referred to as great circles. In conversation, everybody, if you use the word meridian, you are referring to a time zone. Longitude lines are used to create time zones. If you use the word great circle, you're talking about the shortest distance between 2 points on this earth. If you remember from 8th grade geometry, everybody, the shortest distances between 2 points is a straight line. You guys all been through that before. However, you do not live on a flat piece of paper. You live on a round, three-dimensional object. The shortest distance between 2 points on the earth is a curved path, and it's called a great circle path. Okay. Normally I would explain to you how this works, but real quick, because I don't have access to a dry erase board or anything, but imagine this, everybody. If you're taking off out of JFK Airport in New York and your purpose is to fly to Germany, you do not fly directly over the Atlantic Ocean. That is not the shortest way to get to Europe. The shortest way to get to Europe is to head north towards Greenland and then come down over England into Europe. That is a great circle path. If you flew directly over the Atlantic Ocean, everybody, that means you would have to fly over the bulge of the earth. And by going up over Greenland, the easiest way I can visualize this for you, let's just say you're standing on the line of a football game, and in front of you is this big 300-pound lineman who's protecting the quarterback. Now, you're not anywhere near the size of this 300-pound guy, but you're a hell of a lot faster than he is. So I think it's pretty common sense. You are not going to get past him if you try to run directly into him, are you? The shortest, easiest way to get around him is not to run around him because he's a big guy. The shortest, easiest way to get to the quarterback is to jump over his shoulder. That would be a great circle path. And that's what it's like when you fly up to Greenland and then down over England into Germany. You don't go around them, you go over them. Okay. So meridians are time zones. I said earlier that the math was real easy. We just took a long time to invent the clock. Here's the math, everybody. Even though the Earth is not a perfect circle, the proper shape of the Earth is referred to as an oblate spheroid. The word oblate is O-B-L-A-T-E. Oblate spheroid. The word oblate is a real fancy way to say flat, and then spherical, obviously round. So the Earth is an oblate spheroid. Where is it oblate? It's oblate at the North and the South Pole, and its spheroid shape is in the equator. But for the purpose of my explanation, everybody, let's assume that the Earth is a perfect circle. No matter what size the circle is, everybody, isn't every circle 360 degrees? Doesn't matter what size it is. It could be 1 inch or it could be 10,000 miles. It's 360 degrees. How long does it take the Earth to rotate once 360 degrees? 24 hours. So if you divide 360 by 24, what you come up with is every single hour, the Earth rotates 15 degrees of longitude. 15 degrees of longitude is equal to 1 hour of time. And because we are an even 24,000 miles around with a 24-hour day, 15 degrees of longitude is 1 hour of time, and it's 1,000 miles. So far, I've given you the fact that Visalia-Hanford is located at 36 degrees north latitude. Your longitude, it's not precisely this, but it's pretty close. Your longitude, everybody, is 120 degrees west. That's where you are located. If you took 120 and divided it by 15, you come up with 8. There's 8 hours of time difference between you and London. So right now it's 2 o'clock in the afternoon. In London, it's 10 o'clock at night. Each time zone is 1,000 miles wide. London is 8,000 miles from Visalia. That's how that works. The math is simple. It was the technology that took us until 1763. Now, before I let you go for today, everybody, there's one little bit of serendipitous type info I want to pass on to you here. It was just sheer coincidence that this man built the clock in England, and thus you and I are now living in the Western Hemisphere, and the other half people are living in the East, right? Another way to put this is if you're living in the Western Hemisphere, you are, those of you who speak Spanish, you understand this, you are living in the Occident. If you live east of that line, you're in the Eastern Hemisphere, and you are in the Orient. If you speak Spanish, everybody, and you use the word Orient, it merely means you are on the east side of something. That's it. The same thing's true with Occident. It merely you're on the west side of something. It has nothing to do with race or ethnicity. Can you imagine if the guy that built that clock was from Vietnam, and in honor of his accomplishment, we ran the line through Hanoi? That would make you Oriental. Is that bizarre or what? Would it change your race or ethnicity? Hell no, but it would give you a different title. People would call you different. And we humans love titles. We love labeling people. And that would make you Oriental. Imagine how the planet would change in its race relations if we were Oriental and those people living in Asia would be Occidental. Because you don't hear Asians often referring to us as Occidentalists, they refer to us as Westerners. Yet we don't refer to them as Easterners, we call them collectively Oriental. That would make you Oriental. Think about that the next time you're out at 2 o'clock in the morning, you got a serious case of the munchies and you're out looking for Oriental food. In this particular case, you would be looking for Occidental food. All right, I'll see you guys next Tuesday.
Recording stopped.